So we defined space curve. So if you just kind of do it here. Thankfully, its derivatives is pretty easy. The derivatives of dots of things and so forth were pretty straightforward. Let me see. Trying to see where we left off. Yeah, we did all that. Good. Okay, good. And I think the very last thing I did with you guys, so the R prime was equal to F prime, G prime, H prime, just adopting the shorthand way to do that. Exactly what we would hope. So chain rule comes into play. If it's R prime of some function of t, there would be a chain rule piece that would happen. If I have two space vectors that I'm crossing or that I'm dotting, then the derivative rules incorporate the idea of product rule, thankfully, which is really good. Yes? Okay. So I had that big old list of differentiation rules. It's in the book also, so you can get that from either place. Today we're going to look at something kind of nifty. The last thing we did last time was we said if the length of the space curve is constant, then what's true?
And it's an analog of a circle in any dimension.
Yes. And this means across the entire curve. Yes? Okay. Because today we're going to talk about something about at each point on any space curve, I can talk about a related circle at that point on the curve. It's going to be nifty. We'll have some visualizations for that. Then R and R prime are related how? Does anyone remember this? Yes, so if you keep in mind a circle is the greatest example of something that has a constant curvature, constant radius, then at every point the radius and the derivative of the radial function, vector function, are orthogonal. Okay, let me stop for a minute. So as you move around a circle, you basically have this is your R prime and this is your R. It just does that as you go around. Do it again. Oh, sure. Okay. I don't know if I have a quick visual of this. There might be a decent, instead of me using my finger and my pen, let's see if they have a different picture of this. Yeah, here we go. Here's a nice 3D one. Okay. Raw. Okay. Focus. There. So there's your R of t, and there's your R prime of t, and they're perfectly perpendicular. If the curvature changed, then the angle wouldn't stay 90. Okay. So as I go around any space curve, as I move, the curvature might change. And what's really trippy is there are three directions I could talk about curvature. Yes? And that's why the invention of a vector to keep track of the information in 3D and then looking at how to do calculus to it is so important, because there's no way I can consider all different possible ways it could curve all at once. This is kind of like a nice mathematical object that we can use to do that for us. Okay, maybe. How are we doing? Okay. No. All right. So far, so good. That's basically the last thing we did. So today we're going to kind of build up to a more, this still doesn't talk about curvature directly. This just says that if the radius is constant, then there's kind of an idea of the curvature staying constant. We haven't defined what curvature is yet, right? So that's part of what we're going to get into right now, eventually. Okay. Oh, that's right. I should have printed those out. That's okay. We'll be okay. So back in chapter 10, this is back in Calc 2. You guys should have at some point identified the length of an arc. Back then, to make it more specific, the length of a plane curve. back when you did parametric functions back in calculus 2. And just really quickly, if I'm in a plane, I'm only allowed to be in a plane. Back in Calc 2, you weren't talking about 3 dimensions yet. What's up, guys? You guys good?
I'm just asking, I don't remember.
Okay, I'm going to kind of bring it back. I'm going to re-derive it very quickly. If I'm going around some curve in a plane, and I want to know about how long is this is a really cool idea. If I kind of focus in, as I move along this, I'm moving a little bit in the x direction, a little bit in the y direction. So if I kind of blow this up, so there's a curve. Here is the kind of approximation to that. Yes? This is a infinite zoom, by the way, because I'm going to consider this to be dx and this to be dy. Can anyone tell me the length of this? What is the length of this?
1/2 dx dy.
Do it again, sorry.
1/2 dx dy.
No.
Square root of that.
Yeah, what's the old Greek dude that comes into play here?
Pythagorean.
So in this case, dx is of course the infinitesimal direction step in the direction of x. Dy is the infinitesimal direction step in the direction of y. But they are just sides of this little triangle. They are distances on this triangle, yes? Okay, I like it.
B squared plus C squared. Pythagorean
Totally,
theorem.
it's good old Pythagorean theorem. So the length, let me call this, I don't know, let me call this L. The length, in fact, I'll call this L, you can do it, Jeff. Li would be the square root of dx squared plus dy squared. Is that cool? Maybe?
Yeah.
Okay. If I add all those up, I will eventually get the whole thing. So I want to integrate all those little components as they move along. So that's basically what this is. The step we're missing here, let me see if you guys are cool with this. All right. If I look at, if I do this, is everybody cool with this so far? I don't know if you've never seen this before, but I'm hoping you saw it and you just forgot it maybe from chapter 10. This is back when they talk about arc length of the parametric curve. Okay. Even if you've never seen it before, how are we doing with this picture right there? I really want this to make sense. If I want to know the total length from here to here, don't I just add up all the little increment lengths as I move? And that is an example of one of the little incremental lengths. So if I add them all up, and how many are there? Infinitely many. So what kind of a sum do I need? The infinite sum. So I need the freaking s that we just elongated to make into this stupid symbol. Integral. Okay. You guys know that's all it is, right? Okay. Now, does that look like that? That looks like that? Exactly? Close. Okay, so let's get it here. So if I look at this, what if I, let me see if you guys call this. Can you factor, let me see, how do I say this so you guys don't freak out? Okay, up here, could somebody factor an x out of this for me? If you take an x out, what are you left with?
1 is 3 over x.
Kick ass, yes? Now I want you to factor a dt squared out of this for me. So if I factor a dt squared, what happens to each one of these? Same way that had to happen to this poor little dude, yes? What happens? Yes? And of course, what's the square root of dt squared? Assuming dt is positive, or I was thinking about moving in the positive time direction. Okay. And then if I call x of tf and y of tg, There it is. So this is written non-parametrically, and this is now in the form where I can handle if it's written parametrically. Okay. And of course, we all know that our space curves are written parametrically, or at least they can be. Okay, so if I am given a space curve, this is trying to be a T here, by the way. And I want to figure out its length. The first thing I've got to realize is, let's say length from A to B. Amazing. So X is f of t, Y is g of t, Z is h of t, yes? So all I have to do is, it's basically this exact same thing for a plane, I just have to give it one more dimension, right? So this would be square root f prime of t squared plus g prime of t squared plus h prime of t squared dt. How are we doing so far? So I haven't taken a huge step here. This is the parametrization of this space curve. I know how to find the length of a curve that's written parametrically. X equals f of t, y equals g of t. X, y, z, Pythagorean is nice. He's, you know, even though he stole all the shit from his followers, he still says, oh, you just add on extra dimensions, no big deal. Can anyone tell me, all right, real quick, how do I say this? What is the, first off, the components of this are of course related to r prime, yes? You just didn't write the t's, Jeff, don't write it now. There you go, buddy. So the components of this are related to r prime. Can anyone tell me what this whole damn thing is related to r prime? What do I do to r prime to have this come out? What would I ask you about r prime to have you give me this? The length, this magnitude, right? So this, I could rewrite this integral as the integral a to b, the length of r prime. Why do you look like an F? I don't know. What happened? Is everybody cool with me up to here? Is everybody cool with me up to here? Okay, good, because nobody said a damn thing. Okay. Help me out. Help me out. This is why I was wondering in my head how I should do this. Here's r prime of t, yes? Is that cool? This is r prime of t. All right. Can you guys, everybody who didn't like what I wrote down, can you please, dadgummit, can you please figure out the length of r prime? What would the length of r prime be? F prime squared plus g prime squared, and that's exactly what's in here. Yes? Okay, I like it. Let me stop for a minute. This is a really good example of stuff we've done before. I can put in the form of vector terminology just to contain all the information more efficiently. That says the same thing that does. Okay, I like it. And that's what I was saying earlier about vectors are just really good at manipulating multiple pieces of information at the same time. Okay. Now, do you guys remember the fundamental theorem of calculus? Good. I was waiting to see who would ask. The first one. You don't have to remember the specifics, right? The second one was huge. The second one told me how to freaking integrate something and how it relates to the antiderivative. That's the big, what I call the big ass f of b minus the big ass f of a. Yes? The integral of little f from a to b is the big ass f of b, and the big ass f is the antiderivative. Is everybody with me? You guys remember those days? Okay. So what I'm gonna do is I'm gonna define an arc length function like this. And to be better than this, Jeff, let me ask you this way. What have I done wrong? I lost my own narrative. So the main thing from FTalk was if that's now where the variable becomes, I need this to be a different variable. T can't control two different aspects of the same thing. So let me try this again. It's not even what I have written down. I'm not sure what I wrote there. Okay. So remember, that's the weird thing about FTalk 1 was it was the interval a to x, f of t dt. And explaining why it was a t took a little bit of time. So this is a integral function, because our variable is actually one of the limits of the integration. Yes? Okay, let me stop for a minute. So this is arc length. Can somebody tell me then, according to FTalk 1, what is ds dt? Yes, the length of r prime evaluated t. Yeah, that's FTalk 1. FTalk 1 is the relationship between an integral and its derivative. How to take the derivative of an integral. Yes? The minute we find out that the derivative of the integral is just the function inside, that leads to FTalk 2. Well, then the integral itself must be the antiderivative. Okay. You know, like we lived through that once, Jeff. Okay. So now I have a relationship between r prime and the rate of change of the arc length. So really what this is, I could have a space curve defined in such a way that it goes slowly at first, and then it picks up speed, and then it goes slowly, and then it picks up speed, yes? So this would be how quickly that arc length is increasing or decreasing, or how quickly that arc length is changing. And at some points it could be changing much faster than other points. And that's what that captures. Okay. Blah, blah, blah. Oh, that gets a little weird. Let's see. All right, here we are. Yes?
What would the length of that information give us? If the r prime is the information how quickly the slope changes, what would the length of that information give us because we're taking the length?
Yes.
So why are we doing this? Like, what would it even like represent?
Well, like right here.
I understand the length of the curve.
So let me try to say it this way. I think I
It's
see
like
what you're
taking
saying.
the length of the speed. You know, for me it does make sense.
This is how quickly the arc length itself is changing. So of course the answer should give you some kind of a speed.
Mm-hmm.
Yes? Does that make sense?
Mm-hmm.
Okay. And integrating a rate of change ends up giving me the actual full amount over a certain time, right? So if I know how much my position changed from A to B, if I integrate it, I get my actual total length of travel.
Mm-hmm.
Okay, good. So what this is really doing is it's saying this is a little increment of the arc length, how much it changes, yes? And it's equal to the speed at which the space curve is moving in that region. Let me think, how else can I say that? Not sure. Let me think. So if I integrate this over the interval, I will get the length experienced.
Yes.
This gives me a unit. How do I say this? This is going to come up. This is the little bit of thing I just decided not to talk too much about, but I love it. This actually gives me a natural unit to kind of keep track of my length. It's based on the arc length and how quickly it's moving. So I could parameterize the arc length, the length of the curve, in terms of the arc length units. I might try to do that in a bit. We'll see. It's a little bit messy. Okay. Let's see. Maybe this will come out here in a minute. We'll see how this comes into play in a minute. So at the moment, we could consider this just a generally good thing to know. We're going to get into the curvature of a curve now. Curvature of a space curve. That makes sense. This is what I've been teasing for a while. And real quick, here's the definition of a smooth curve. If I have, and this should feel very familiar to things you talked about in Calculus 1. If r prime itself is continuous on some interval, and r prime is not 0, then this curvature, we have a smooth curve, and the curvature is a measure of how quickly the curve changes direction. And like I said earlier, it can change direction in 3 different ways. So the curvature is a measure of how quickly it's changing direction. So if I have a straight line in free space, what should its curvature be? 0. It's not changing direction at all. If I have something that's changing direction in a plane versus something that's changing direction the same way in the plane but also changing direction out of the plane, wouldn't the curvature of this be a little more than the curvature of the one that's just in the plane? So that's what I mean. I have different ways I can curve. So I could curve in a plane like that, or as I'm doing that, I could also come out of the plane. So I'm adding another dimension of another thing curving. So if I'm in the plane, isn't my z component not experiencing any curve? But if I do that same thing, but I go up at the same time, now my z component is going to be adding some curvature, some idea of curvature to it. Okay.
Total curvature is the sum of the curvature in each
We'll get
direction.
there. But you're thinking the right way. Okay. So if I take, let me remind you guys. Somebody remind me, and I'm pretty sure this is what I was looking for. Yeah, we defined at some point. Oh, by the way, let me finish this out. I just said this, but let me write this down. The curvature measures how quickly the curve is changing direction. And that word direction has a lot of stuff going on because it can change direction in a lot of different ways. Because we're not just restricted to a plane now. I think, remind me about this, I think last time I defined the unit tangent vector. So let me see, maybe I didn't.
Yeah, you
I did, okay, good. So the unit tangent vector, what was that?
R prime over the length of
Yeah, it kind of makes sense. R prime is pointing in the direction of the tangent vector. And if I have a circle, that's always perpendicular, but it could, if I don't have a circle, then it doesn't have to be perpendicular to the space curve itself. Okay. If I divide, obviously, by its length, I get a unit vector in that direction. So that's what we call the unit tangent vector. So just like in Math 180, when I take a derivative of a function, it applies to the tangent line at the point, right? The derivative itself was kind of like a directional idea. So the same thing here. When I take a derivative of the space curve, I get an idea of a tangent direction. If I divide by its length, I get a unit tangent direction, which we already said in general is more useful to know. I can build off of that easier, which is why we make a lot of unit stuff when we can. So now that we have this little reminder, here's what curvature is. So of course curvature starts with the letter C. So we're going to use the letter K for curvature. And let me just write this down and see what you guys think. It is the rate of change of the tangent vector with respect to the arc length. I don't think there's a great picture to give you about this. No. So as the arc length changes, so I can consider ds to be a way to measure the motion of it based on how quickly the thing is moving. So as that changes, how much is my tangent vector changing? So if I'm going in a straight line, how much is my tangent vector changing? Not at all. So the curvature would be 0. If I allow that to change, but just in one dimension, then it's going to be changing, but not by as much as it could be. So that's why if I'm moving and my tangent vector is changing as I'm going along my path, that is the curvature of that space vector. T is a 3-dimensional vector, correct? So it's got information about all the components. So if I include curving upward also, then that's going to increase the curvature based on just going in a plane by itself. Okay, maybe. This is trippy. This is really trippy. Yes?
What kind of values will it store? Is it going to be the same as slope, or is it going to be something different?
So the minute we're in 3 dimensions, when you say slope, that doesn't quite apply. And that's why
Slope in 3
I'm with you.
directions.
So like the vector of the
Yeah.
direction.
Mhm.
Yes? So just ask your question again.
Would it be, which information would the curvature variable store? Is it going to be the same thing as the slope of this 3-dimensional vector?
Sort of.
Okay.
Okay. It's related to that. It's a little more than that. Because it's actually the rate of change. So it isn't a. All right, real quick. In Calc 1, do you see how t itself is already a derivative?
Mhm.
Aren't we taking another derivative on top of that? But with respect to s, correct? So it's not a pure second derivative, but in one sense, it is a second derivative. Do you see that? T is a derivative of r, correct? Am I not doing another derivative of t? So isn't that like the second derivative? I really want you guys with me. T. What was t again? It's r prime divided by the length of r prime, right? So isn't there a derivative of r already with t? That's the first derivative. Isn't the curvature another derivative of t? Isn't that related to a second derivative of r? In Calc 1, what was the second derivative? What was the second derivative in Calc 1? Cup down, cup up. Concavity, which is a kind of a measure of curvature. Holy shit. So concavity in Calc 1 is a simplified version of this. So, but it's not a straight second derivative because it's according to s, yes? But still, it does contain an information in it. Okay. Do you see why I couldn't answer your question directly? Okay. But that's beautiful. I love that you brought that up because now I can just say that now instead of later. It kind of reduces to the concavity if I restrict my stuff to 2 dimensions. Yes?
So we just consider ds to be arc length.
Do it again?
ds is arc length.
Yeah, ds is an incremental change in my arc level. Yeah. So as I move along my trajectory. Now, remind me again, what is our space curve? What's the variable in my space curve? That's a really weird way to say this, but what's the variable in my space curve? It's r of t. This sucks then, because my space curve is not a variable of s. So remind me, t is r prime divided by length of r prime, correct? That's a function of little t, correct?
Yeah.
And this stupid thing wants me to do a derivative with respect to s. You guys see the issue with this? This is what I call a conceptual formula, and now we're going to improve it.
Sure, but isn't ds with respect to t?
ds, yes, and now we're going to bring back what we just did a minute ago. Okay. We're going to kind of do it first a little, we've done this kind of thing before. So let me just look at the inside of this. We're going to do something like we've done before. dtts. Isn't that equal to dt ds? I'm sorry. I'm starting with where I want to end up. dt dt. Okay, that's where I want to be, isn't it?
Times dt.
This is equal to dt ds times ds dt. You've seen this kind of thing before because these would cancel out, so of course they're equal to each other. Put a little vector sign over that. Yes, sir.
Is that big T or little t? On this,
Which one? Down here?
Up there.
Up there.
Big T?
Big T, yeah, sorry. I always try to make my little t have the little curvy dude at the bottom. Okay. The little t's look like umbrellas. Let me stop for a minute.
So it's dt ds.
You're never gonna have to do this yourself. We're deriving some stuff. We're gonna end up at this little crazy little formula that I'm not gonna make you memorize, but I want to show you where it came from. Yes? So is everybody cool with the fact I got functions of t and then this dumb thing, curvature, it has to be defined the way it is, and it wants ds. I don't have it defined in terms of s. So I'm trying to kind of rewrite things so I can use this instead. So remember k was this. Which I can now write as this. And who remembers what ds dt was from a little while ago when we first did? Yes, this is the length of our prime. So now I can have, by the way, this is kappa. I don't know if they tell you that. Who knows? This little letter here is the Greek letter kappa. This is true, so I can plug this in there, and so I end up with just this. I end up with kappa is t prime of t over r prime of t. And now everything's in terms of little t. So that's why I can go back to prime notation, because now I know it's the with respect to t. So now it's much more in your face. Yes, Stan? The top of that is effectively the second derivative of r?
Yep.
Yes, but now it's divided by r prime. It's not exactly perfectly that. Okay. So if I'm given a space curve, I calculate t, I can then take its derivative, and I can divide by this and get the curvature. Now, even this is horrendous sometimes. And you're all like, yeah, I'm with you on that, Jeff. But trying to do a problem using this format gets a little disgusting. So here is another way to write it. I'm not sure if I want to, let me see. Sure. Do you remember that, in fact, I don't think we've done that yet. No. Let me see if I could piece together a little something for you here. There it is. Terrible thing about looking for glasses, you need your glasses, fine. Yeah, okay. I think we did that yet. There it is.
Blah, blah, blah.
Yeah. That's a little gross. I'm not going to go through that. Alright. There is a sequence of steps I could take as a proof. I could prove that t prime of t, I could prove that this equals the length of r prime cross r double prime divided by r prime squared. We could do that. I'm not going to put us through that. It's actually, there's a proof on page 907 in the book. You could step through that if you'd like. So I could rewrite kappa, did they even tell you that? No. As r prime of t cross r double prime of t divided by r prime of t cubed. Yes. So let's do an example. Oh yeah, okay, good. Just here. I mean, I could step through all the steps. There's a little proof at the bottom where they kind of end up with t prime equals this business. I don't think the steps of the proof are very generally illuminating. Yes? Oh, sure. On a circle, all right, no. Let's do a concrete example. Okay. Let's do a concrete example here. So everybody got what they want from this here? Just to remind you guys, I'm not going to make you memorize this. There's enough work involved here that forcing you to memorize it really is a little beyond the pale. What we're building up to is, if I have an object moving, its motion determines a reference frame for itself. So we are developing slowly the axes for that reference frame. So kind of, if I'm moving in a plane, I can consider this to be the origin. And so my x-axis moves with, you see, if I curve this way, now my x-axis move that way, and my y-axis would be orthogonal. You guys kind of with me? So now just extend that idea to 3 dimensions. So now I'm going to need something that's tangential to my motion, something that's normal to that, and something that's normal to both of those. Yes? And the direction of this one has to do with which way I'm turning, which is kind of neat. So at every point of the trajectory of a particle or whatever, it's got this little, you could do it, Jeff, this little inertial frame. This little, what do you want to call it? Not an inertial frame, but it's a frame of reference. It's a coordinate system that moves with it. Okay. Yes?
So it always, in the reference, will always look in the same axes? So it will never rotate?
Now, as it's rotating, it could speed up or slow down, and the length of some of these change.
Mm-hmm.
When it moves, its main t vector moves, so then that changes where this is pointing.
Mm-hmm.
You kind of with me?
Yeah.
But you can take a snapshot at any moment. If you know the direction and magnitude of those things, you have a lot of information about that object. Yes? Okay. All right, let me stop for a minute. This is very trippy. This is why I have some visualization, so you don't have to watch me do this the whole time. Okay. So this is a very crank it out kind of formula, yes? Okay, you all got this written down? Yeah. Okay, so help me out. Jeff.
Will it be the same thing if you put the axes on the nose of the roller coaster and let it slide?
Yeah. In fact, there are some animations I've seen that basically have exactly that. Is that what you're saying? So, yeah, if you have anything that's moving, you can consider it, yes, totally. So what if I have a space curve? Let's do, let's do this. This is a nice one. Oops, sorry. You're all like, sure, Jeff, can we play? Now, if I want you to calculate the curvature, and I want you to do it with that last thing. In fact, let me see if I can get you guys to agree with me. Yeah, real quick. Let me show you this. What would t be? How would I calculate t? What would I need to calculate t?
R prime, R double
Yeah,
prime.
I would need r prime Alright, so somebody help me out. I'm gonna need R prime anyway in a minute. So let me put down here, I'm gonna put up here put a little note next to this business. Put not the sucky way. Alright, I'm gonna use this definition of curvature first. And we're gonna quickly give up on it. So what is R prime? Help me out.
1, 2t, 3t squared.
What is the length of R prime? Is that okay? You guys with me? So R prime divided by the length of R prime would be 1 over this plus 2t over this plus 3t squared over this, yes? And then what do I need for kappa, for curvature? T prime. Do you see how it's a very simple space curve, yes? And look how I really want you, does everybody see how disgusting it already is? Okay. I really want you to understand why there's a whole proof to rewrite the form of the curvature in a better way, a more workable way. So this is more of what I call a conceptual formula, and the one with R prime cross R double prime, all that kind of stuff is a computational formula. So we're going to give up on this. We have part of what we need though. I need this. Jen. What else do I need for my formula? Let me put it up here. We need R double prime, so that's easy. What's R double prime? Good? Good? Kick ass. How comfortable are you guys with cross products now? Some of you guys, I love some of you guys, I love you guys. Some of you guys are trying to memorize A1, B3, blah, blah, blah. Oh my God, dude. But, I mean, no disrespect. You can do that if you like it. What's the other way to figure out? So, because for the curvature, I need to calculate this here, yes? The length of that cross product. So what's the way to get the cross product? Yeah, IJK, 1, 2t, 3t squared. By the way, would it have been okay if I would have put 0, 2, 6t right here instead? And then 1, 2t, 3t squared below that?
No.
That would have been, in general, that would be bad. Notice this says the length of this, but if you do a cross product, if you change the order, it's the negative of what it would have been the other one. Okay. Where am I at? 0, 2, 6t, and then I can repeat if you want to, or you could. Some of you guys just do the determinant directly. I love it. Whatever makes more sense. If none of it makes sense, come see me. So I would get 12t squared minus 6t squared. Is that cool for I? 12t squared minus 6t squared, yes? Is that cool, everybody? 12t squared minus 6t squared, so I get 6t squared. I, where am I at? 0 minus 6tj, and then 2 minus 0k. Say again?
Would it be plus 60? Because you do 0 minus 60?
Where are we at? For j?
Yeah.
0 minus 60, yeah, so it'd be minus 60.
But times the negative out front. Would there be a negative out front or no?
Okay, no, definitely not.
Okay.
Here's the thing. If you do the determinant the full way, and I mean you would put I in front of the determinant of 2t, 3t squared, 2, 6t, you then have to do minus j, determinant 1, 3t squared, 0, 6t. That's the full determinant. It's really easy to forget. The shortcut, when I do positive, 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 minus, 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 it incorporates that in. That's why it's a shortcut, yeah.
I want to go a little bit back if you can. How did we get T prime, the big T prime, with the cross product?
Oh, that was you mean right here,
Yeah,
going from here to
Yeah, how did we get the cross product?
this?
Yeah.
We didn't!
Okay.
You called me out. That's why I brought the book over and I said, I could just write this proof down, but it's here already.
Oh.
Yeah. And there's no part of it that's like immediately generally applicable. So if you want to, you can follow this along. So they develop R prime, they develop R double prime, and then they cross it. So it's kind of a brute force deal. Yeah? And then eventually they get the form of it in a better format. So they get what T prime is, and then they plug it into the curvature. Yeah, it's not the most exciting proof, I would say. It's just a brute force deal. So now what do I have to do with that vector that we just got? Find the length. Good. So how do I find the length? That's why I put a little arrow, because I'm not really counting. So the length of this. Square root of. So I want to find the length of this, yes?
6t squared.
36t to the fourth, yeah? 6t squared squared, yes?
That's
Square each component, that's how I find every, yeah, plus 36t squared
plus
4. Stop for a minute. So if I give you r of t, how difficult is r prime of t? It cannot be. Derivatives are always easier, yes? How difficult is r double prime of t? See my first note, yes? I'm not going to give you space curves that have like multiple quotient rule bullshit. I mean, that's just, you guys kind of with me? So finding those are relatively easy. Finding the length of any vector, I keep pointing at that. Finding the length of any vector is easy. It's always the same thing. The square root of each component squared added. Yes, that's the length of the vector. Yes? Yes, sorry.
Not to derail a bit, but were you saying it was a shortcut for cross product? Or what?
That was it. That's it right there. That's the shortcut. Yeah. Is that okay? Cool. Okay. Yeah. If that's not short enough, then you haven't done enough math. Yes.
How did you get those numbers from the matrix determinant?
Which number? Sorry.
The 6t squared.
Okay. So again, the shortcut. But look at my eyes. This is positive 12t squared minus 6t squared. That was the shortcut I showed you. So if I write it, and then I repeat the first two columns, positive, 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 negative, negative, negative. You don't have to do it that way if you don't want to. If you know how to do determinants and you'd rather just do the determinant directly, feel free. If you'd rather memorize the cross product formula, A3B2 minus A2, I don't even know. Right?
It's A2, it's A2 minus B3.
I don't care. But yeah, okay. Thank you. If you got it memorized, you're good. You're fine. I don't feel like doing that. I don't like memorizing shit if I don't need to, but you totally can. Okay. Is everybody with me so far? So listen. What did I say about the curvature formula? Do you have to memorize it? No. I'm going to give you the curvature formula. I'm going to ask you, hey, for this space curve, find a curvature at t equals 3. You're going to find r prime, you're going to find r double prime, you're going to take the cross product, you're going to find the length of r prime, you're going to cube it, you're going to divide them, and then you're going to plug a 3 in for t. Yes? So it's really just, I'm not going to give you a ton of those, because then it just becomes a little show off that you know how to get lengths and cross products and stuff, right? So I'm not going to give you like a ton of these. That's kind of silly. But then I would ask you, explain what your answer means. If you get a 0, that means at that point what's true. So for example, do you guys know what a cube root function looks like? If you graph a cube root, x to the 1/3. Yes? Right here.
Right at the origin.
What's true about it?
It's 1.
At that moment, it's a straight line, correct? So the curvature right there is 0. You guys see what I'm saying? So if I give you a space curve and I ask you to calculate the curvature and you get 0, that means at that instant, it's a straight line. It's not curving in any direction at that instant. Are you guys kind of with me? I like it a lot.
Is there any limitations to the curvature? Any maximum or minimum values? Or
No. You'll see. All right. One last thing I've got to do. I've got to figure out the length of r prime. Yes? And I already have that here, yeah? Yes? And so the curvature is this divided by this cubed. This divided by this cubed. So the curvature will be say again, sorry.
I was really scared of like how I was gonna apply this for homework as we were writing it, and now we do examples.
Okay, good. It's always nice when I do some concrete examples. Just ask my linear students. They love them. Let's see. Oh, good. Okay. By the way, what is the curvature of this at the origin? And looking back, the space curve is this, yes? So notice what I just asked you. What is the curvature at the origin? So what's the value of t for my space curve to be at the origin? 0. So do you see the level of question I could ask you? I didn't tell you the value of t. I said, what is the curvature at the origin? You got to look back at the function and say, okay, when is it at the origin? If t is 0. Now, how do you figure out what the curvature is at 0? You freaking plug 0. What do you get when you plug 0 in? 2. Okay.
How did we get to the bottom of that, okay?
That was the length of r prime cubed. Yep. The length of r prime cubed.
Okay.
And we'd already done the length of r prime in our first failed attempt
Yeah, makes sense.
when we gave up on this guy.
Okay.
Yeah.
Thank you.
Okay, I love you guys. You guys okay? So again, there's a lot of derivation. There's a lot of weird concepts. But it boils down to nuts and bolts. Now, you do have to be able to explain the results you get, but not excessively, because we haven't worked with curvature much. Yes?
Yeah, I was just gonna ask, like, when you get like k equals 2 or whatever, like, what does that mean?
Good. If we do more functions, we start to get a baseline of what it means.
Okay.
Yes? Like if I say slope 4 and slope 5, I have a visual of what that means. Curvature I don't have because we haven't used it much. Okay. Okay. Blah, 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 blah. Real quick. Here, let me give you just the results, because, by the way, let me give this to you. Ooh, that's right. So right now we've got this. There is another form. This is not its final form. This would take a little getting, and again, this is just a little side note. The whole point of this class is not to prove the elements of curvature. But I just want to show you another form for this. If I'm given a curve not written parametrically, if I'm given a curve, and this is not a curve, this is like a two-dimensional dealio. Whoops, I got one too many. I'm thinking about linear. Yeah, there's a square here. So the bottom kind of looks familiar. Well, I don't know if it looks familiar to you guys, but if I unparametricize the length that we talked about earlier, it actually takes that form. So this is if I'm given a function just in the xy plane, like this.
Is that like 1 plus?
Yeah.
Okay.
Sorry. Rewrite that again. Poor little guy. This is the concavity divided by the length of the arc that this is tracing. Cubed.
So in this case, the bars are absolute value, not magnitude.
Exactly. Cool. Because you can't have negative curvature. It's kind of interesting. Yes?
Do we need to write 3/2 every time, or why don't we just write it as 1 plus f prime cubed?
Oh, I'm sorry. It should be squared. Now this whole thing,
Putting it on the bottom of the fraction.
this whole thing is to the 3/2 power. Yes?
Yeah, but couldn't we just remove the cube because the inside cube, the outside is root, so
Hell no.
no?
Can I distribute a power?
I don't want to answer that.
So, real quick. You're talking about the square killing the over 2?
Yeah.
Yeah, because I can't distribute the powers. 1 plus f prime squared to all of it to the 3/2 power. And the 3/2 power can't distribute, yeah. Okay. No, but don't get me wrong, I love it. Yes?
Concavity over what?
Oh, concavity over the length of the arc. This is related to the arc length we talked about at first, written in non-parametric form. Just a little side note. So what's kind of neat is blah, 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 blah. Yeah. All right, I'm not going to focus on this too much. If you take the derivative and you take the second derivative, you've got everything you need to throw into this, and then you can calculate the curvature, what the curvature would give you for a parabola. Now, real quick, where's a parabola the most curvy? Yeah, at the bottom. So at the, if it's a y equals x squared, it would be at the origin, correct? So let's see, real quick. Just to kind of answer your question, Jake. Can you guys help me out? Well, I'm going to do this real quick. Yes? So this will be the length of f double prime is just 2, not the length, but the absolute value, divided by 1 plus 2x to the 3x power. That is the curvature at any point.
4x squared, not 2x.
Oh, yeah, thank you. I keep wanting to not square it. Okay, squared, yes. What do you get when you put a 0 in there? You just get 2, yeah. And if I put anything other than 0 in there, the answer will be less than 2, yes? So it is the most curvy at 0, yes? Now, real quick, how can I make it even more curvy at 0? I can make the parabola go up higher, quicker, yes? So if I do all this again for like 8x squared, you can kind of follow through and you can get a feel for kind of like, so we have, how much have you worked with the idea of curvature that I presented here today? About that long, you know? So you have no feel for like a parabola that x squared versus a parabola 1/2 x squared. Wouldn't 1/2 x squared have less curvature at 0? It's flattened out a bit, yes? Okay. You guys semi with me? Screw you, Jeff? Yes.
Are we only doing this with squared? Like, can we do it with x cubed?
this formula for a function in xy plane works for any function you give me. So I can figure out the curvature of the sine function at any point. Yeah. Yeah. Okay. All right. Now we have this idea of curvature, and we built that idea from this idea. So we've got this guy. And I think you guys would all agree with me that this guy is silly important in terms of trajectories of particles or of spacecraft or whatever. You guys with me? Because of course, what does that tell me again?
Direction, what's heading, tangent.
Direction and setting at any instant in time.
Yes.
And in fact, this is the unit tangent vector. So it's kind of like just a directional indication. I've stripped it of magnitude, poor little dude. What if if I have a single vector, I can always figure out a normal to that. So you guys remember in Calc 1 that sometimes you had to find the equation of a tangent line, and every now and again they ask you to find the equation of the normal line? Does anyone remember that? The normal line? Yeah, very rarely. Very rarely. This is true, which is unfortunate. Anybody ever taken any physics? If I have this, this is sitting on the thing, what's pointing up? The what force? Normal force. It's normal, it's perpendicular to the surface, yes? That this thing is pressing on. So it's normal, it's all about being perpendicular. So if I have a tangent vector, I should be able to calculate a normal vector. Does that make sense? Sweet. Oh, let's see. Do I want to do all that? Yeah. Okay. So let me do a couple things. Can you guys tell me what this would be? Yeah. Good. Good. T is the normal vector, so its length would be always 1. Yes. So if real quick, little side note, if I have r of t, just to bring this back for a second. If r of t is a constant, r prime of t is orthonormal, or orthogonal, or perpendicular, right? So let's just say orthogonal to r. Okay, let me stop right there for a second. Oops. What that leads to is, let me see if you guys pull this. T prime dotted with t is 0 in this case. And that's, again, if my radius stays constant, then it's always orthonormal or orthogonal or perpendicular to the r prime vector, which is related to my t, so it's always orthogonal to that. Okay, it's a little side note. So my normal vector, we're going to define this to be t prime divided by the length of t prime. And the reason we do that is because then it's orthogonal to the actual tangent vector. So I said earlier, if I have direction of motion is my tangent vector, I want a vector that's always orthogonal to it. I'm going to define that to be my normal vector. And now I have one last vector to describe, and then I've got my 3 that I was talking about earlier that kind of move along with my object.
So you want the cross of T and M? Because that would be
Ooh.
perpendicular to both.
Look at you getting ahead of me. So the last little dude we're missing, we're going to call it the B vector, because to be honest, It's called the binormal. Why do you think I would call it the binormal? Well, if normal is kind of like another name for perpendicular, B's got to be normal to both T and N. So we call it the binormal. And so we call it the B vector because we're very creative people. Can we stop for a minute? I have a direction of motion that's related to T. I have a normal vector to that sets up sort of like a plane of motion. And let me stop there. Let me show you this. Let me show you a visual of something. Let me show you just that, if I can remember which one is which. So here I have, real quick, I showed you a picture of this before. What do you think that purple vector is? What do you think it is? T. Oh shit, it stopped. Now, purple vector is still T. What do you think that blue vector is now? Now, I really want this to make sense. Oh, I should stop it somewhere where it's in the middle. So it still exists. Okay, there it is. All right, come back to me. Stop. Go forward a little bit. Stop. That's not too bad.
Binormal would be the point between.
Okay. So, you see how he says, if I stop it right there, the direction of motion is, if I have a function in 2 dimensions, x, y, you with me? The slope, you could create a tangent line to that curve, yes? And so near that point, all the function values kind of like, at that point, they are on this line. At this point, the function values are on this plane. Okay, maybe. So it kind of incorporates if it's going up or down or not. So it kind of incorporates what it's about to do. That's what derivatives really are all about, yeah.
It's a little conceptual. So let's just say the dot is Earth. Is that like gravity pulling? Is that the same vector? or
No.
is that-
No.
okay, so- Got it.
This is completely due to its motion. There's a separate vector with magnitude depending on the force that's causing it to make that circular motion.
Okay.
But I appreciate that. Okay. This vector's direction is completely dependent on which way this guy's going. The force due to making something move in a circular motion is always pulled directly towards whatever's causing that force, like pulled toward the sun or something, the center mass, yeah. Okay. Yes, oh, here. Oh, there's a hand. So these follow the right-hand rule is what this guy's about to say? Yes?
Can you use both of those vectors to predict where it's going to end up, I guess? In the next-
I mean, you could try.
Is that what information gives us?
I mean, what does the slope tell me? A slope at a point, I have to also know that the function is well behaved. Yes? And if it wasn't well behaved around that point, the derivative wouldn't even exist there anyway, correct? So it is sort of useful for predictions. Yes. Okay. So let's finally incorporate this last thing we just talked about. So what's that red vector? Yeah, that's the binormal. I like it. So let me see if I can get this in a better place.
So the length of
okay.
each of these vectors is kind of how much it's changing in each of those
Oh,
directions.
I forgot to write this down. Say again?
So the length of each of those vectors would be the amount that it's moving in that direction. So if
Okay. The amount it's moving in that direction.
So
How
it's-
quickly it's changing in that direction. Yes. Does that make sense? So if I slowly flatten it out so it stopped curving and it just started going straight, then that blue line would eventually decrease to nothing. Yes?
Yeah.
If I stop going up and down, that red line would decrease the magnitude. Okay.
Yes.
So you can get further into the definition of the magnitudes of these and what they reference. Yeah, okay. Coming back here for a second. I think I had, what was this other thing? Oh, we're not there yet. Shoot. I haven't written this down yet. So the definition of binomial, binomial, teaching stats. This is very, very important about the order you do this in. Because of course, if you turn around, then it's going to be pointing in the wrong direction, which is bad. So if you want to, you can think TNT. TNT. I don't know if that helps. That might not help. I don't know. Between. BTN. Between. No? Yes. I don't know how many guys do stuff like that for yourself. That's what got me through a lot of classes, is trying to come up with a story that related to whatever I had to memorize. But that's true. I'm not going to necessarily make you memorize this, so you're okay. This is the most directly defined vector. So the vectors we've already defined in the cross product, because it just has to be normal to both. The other ones were definitely trippy to get there. Yeah, so already talked about the idea of a normal plane. Well, I sort of did. Let me kind of define this better. So I can have a normal plane. Now, normal plane would be defined by B and N. Now here's what gets interesting. So the normal plane kind of makes sense. It's got to have the normal vector in it. And it's kind of like the plane that's perpendicular to what I'm about to say. There's a really weird word for this. And this is called the osculating plane. This one is defined by T and N. Now this one makes sense. The B was the last thing we defined. T was the direction of motion. N was orthogonal to that. Together they make a plane, yes? And that was a plane I was saying that it kind of like is locally where my function values are contained. They're contained in this plane. The same way that locally my function values are defined by that straight line. In the same way. It kind of makes sense. I step up dimensions. Whatever was a line is now a plane. Okay. It. What this then leads to, and this is kind of like what came up earlier, at every point in my trajectory, I could talk about the circle of curvature. And I think, yeah, this is a circle in the osculating plane with the same curvature as the space curve at that point. So let me show you a picture of this weird dude. Ready? Let me start him over. All right, now watch. So right there, the curvature at that point, if I just kind of continue to draw it out, it makes that circle. That circle lives in the plane. Now, of course, this is a 2D picture, so it's a little, it's a little more boring than it has to be, but I couldn't really find a good 3D osculating circle picture that you could really tell what was going on. Notice when it gets to a point like there. What's this point? That's the who to what point? Sure, but in terms of the curve, in terms of the second derivative, inflection point. At that point, for that instant, isn't it straight? The function itself is straight, infinite, right there. More than like a tangent line idea of straightness. It is not curving because it was curving one way and then it's curving the other way. So of course in the middle, it's not curving at all. So watch what the circle does as our point approaches that inflection point. Yeah. Then it's like the poor little dude straightens out and then it turns on itself. Let's see, hold on. Turns on itself. There we go. Stop. So the curvature, real quick. Do you guys understand that right there, that is, the bigger the circle, the less curvature? Do you guys get that? I really want this to make sense. So one little thing I didn't tell you, you can write this down if you want to, stopping. The radius of the circle is 1 over k. So the bigger k is, the smaller the radius is. Kind of makes sense. If you're more curvy, then I need to have a smaller circle capture that quick curve you're doing, yes? If you're going, this is not a very good curve, is it? So if I draw a circle, then it's going to be a giant circle. Are you guys kind of with me? So the bigger the circle, the smaller the curvature. So at a point where there is no curvature, the circle becomes a line. And then, of course, my curvature goes the other way, so then it wraps around the other way.
Does it exist?
Say again?
Does it exist?
If the curvature goes to 0,
Then divide by 0.
then the radius goes to infinity, 1 over 0, yes. So you could say it doesn't exist, or you could say what literally happens is the circle becomes a line, which becomes a circle. Yes.
And then the curvature is going to be negative. Right now it's negative or positive?
I wish they would. Wait, look at this. What do you guys think? What went into the formula for the curvature?
I was gonna say the curvature is never negative.
Good. Curvature is never negative.
But it changed directions.
Changes direction, sure.
We don't care.
Curvature is a absolute measurement of curve. So just because I lay a circle one way doesn't mean the curvature changes if I lay it the other way.
So if we just know the curvature, we cannot tell which direction.
Exactly.
Okay.
That's what the other elements are for.
It's like a scalar.
Yeah, sort of. I see what you're saying. Anyway, enough of that. What was the other curves here? Oh yeah, here's a sine. This one is same old thing we just saw a minute ago, yes? But now you can see, now you see everything. I wish this was bigger. Hold on, you could do it, Jeff. No, you can't. There we go. Now, real quick, do you see how the circle, how do you stop this damn thing? Oh yeah, right there, Jeff. Old man using technology. Okay. That oscillating circle is in the plane defined by these two vectors. Yes? Okay. So that's the osculating plane. And the circle that lives in that plane, that's curvature is defined by the curvature at the point of the space curve. Holy shit, that was a lot of words. The circle that lives in the osculating plane, that's defined by those two vectors, also incorporates information about the curvature of the curve itself, of the space curve.
So like if the curvature is constant, then is that like the cylinder that we see going down?
Yeah, I wish, shoot, this one's just some crazy, yeah. If you do all the work for a circle, which I can't remember if there's a homework problem like that or not, but it should make sense that the work for this for a circle would be kind of boring because it's always the same. For a circle, does the curvature ever change? No. So does the osculating plane, well, yeah, a circle has to be in a plane. So kind of a lot of the stuff simplifies because I'm not really in 3 dimensions then. Yeah. But yeah, you could do this on a circle and see what happens. Okay. Blah, 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 blah. Oh, okay, good. Oh, we only have one little thing. I will say this officially right now. Because I'm just going so slow this semester for some reason. We're gonna talk about 13.4, but I'm gonna make the homework for 13.4 extra credit. We will talk about it. There are some really good things in it, but it's sort of like the applications section. So I want to point a couple things out about it, but it's not going to be our next test. I might put a bonus question about it on our next test.
Is which one?
13.4 was about some physics applications. Sorry? 13.4. Yeah. Okay. So the last little idea. That's a weird word. You guys, what does that word sound like? Torsion. What comes to mind with that word, torsion? Torque. Yep, kind of torque. Something about something rotating. Yes.
Rotational force.
Yeah. There's certain injuries that are torsion kind of things. Yes. I don't know if some of you guys have lived through that. I'm sorry.
So, yeah.
You got it. Oh, by the way, I'll put this. The radius is 1 over k. See, I don't want to say too much about this. We actually had this down here earlier today. Remember this? DTDS? This one tells us how the normal plane changes as our point moves along our trajectory. So the normal plane, so if I move in all dimensions, my normal plane could change orientation, correct? And this would give me some idea of how that's happening. If it's 0, obviously that means that it's not changing its orientation. Let's see, how do I say this? BDS. What was B again? Binomial. Binormal. I can't stop that. This ends up being parallel to our normal vector. Now, it kind of, if you think about it, R and R prime are sometimes perpendicular, right? B and N are already perpendicular to begin with. So dBds points in the direction that B is changing. It's going to end up being parallel to the normal vector. So dBds is equal to a, how do I say this? You guys have talked about proportionality. Like if two things are proportional, if x and y are proportional, x equals my, some constant. So since this is parallel, they are proportional to each other. Two vectors that are parallel, one's a multiple of the other one, correct? So this is where this comes in. The way we define it, let me just put it like this for the moment. It's some proportionality constant times the normal vector, and we call this k was a bad choice, I'm sorry.
Yeah.
That's just the one you use for proportionalities. That's the first thing that came to mind. If you want to, you just put like C. So that's the proportionality constant. If two vectors are parallel, one is a multiple of the other one, correct? Okay. I'm sorry. We use the letter K for proportionality all the time. And we choose to call this negative tau. This is the variable of torsion. So it's a measurement of how quickly the binormal vector is changing. The binormal vector, let me see, how do I define a plane? What do I need to define a plane? You can do it.
A vector and a plane.
A vector that is normal or perpendicular. You with me? T and N. All right. I know that there's a lot today. I understand. T is where I'm headed. N is normal to that. That's a plane, correct? B is by definition normal to that plane. It's perpendicular to that plane, correct? Okay. So the amount that this is moving tells me the amount that the plane is moving. If my plane is defined by a normal vector, the amount the normal vector is moving tells me how much the plane itself is moving, because what's the only thing that would make this move if the plane moves? So if I look at dBds, how quickly that is changing, it's proportional to how much my normal plane is changing. That's the whole idea of torsion. It's that amount by which my normal plane is kind of moving. How much it's changing orientation. Okay. Blah, 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 blah. So this is kind of like also twisting. You can think about it like twisting the normal plane. Blah, 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 blah. So if I do some, I'm not too worried about this to be honest, but I want you to know this exists. So if this is true, let's start over again. dBds is equal to negative tau normal, and this is my torsion. Oops, sorry. And if I dot both sides with n, what is n dotted with itself? Not 0, no. Say again. The length squared. The normal vector was a cross product of two unit vectors. So what's the length of the normal vector? 1. Good. So then this would be dv dot n is negative t. And the only reason I wanted to do all that is so I can get this by itself. So you have a nice definition. And, well, if you move the negative on the other side. So you get torsion is equal to negative change in binormal dotted with the normal. Flesh. If I want, like we did earlier, in the interest of time, I could do a lot of little steps to make this look more. Do you see how this is based on ds like before? We could do something very similar to what we did earlier to make it in terms of t. So then I would get negative b of t prime dotted with n. So that's b prime n all over r prime of t. Now there should be, oh, I want you. Yeah, should be magnitude, yes. What kind of an answer will I get here? Will it be scalar, vector? Scalar, and that was weird for me because you can't really divide by a vector very easily. So it's got to be the magnitude. Now listen. We did a lot today, yes? There's a lot of shit today. I want you to understand. Does the basic concepts, the visualizations, does that make some sense? In terms of how I'm moving, I can always have a normal to that, and then I can define a normal to both of those. And that's like my own little independent three-dimensional reference frame I carry around with me as I move, yes? You can think of it as pointing out your eyeball, and as I'm moving, I can have all these other reference frames moving with me. All right, let me stop there. That by itself is pretty nice. The pictures make pretty good sense. Even the weird-ass circle with the idea of curvature makes some sense. You can get very lost in this. You need to know these exist. You need to know how to calculate them. It's just a lot of showing me you understand earlier parts of chapter 12. This is really what this is. It's an application of a lot of the stuff we talked about in chapter 12, correct? So this is kind of like our midway section that's not truly straight applications, but it sort of is. Section 13.4 would be pure application. where you're doing physical, and you're basically doing physics in section 13.4. Okay, so we'll talk a little bit about that next time. Here, let me give you this. I think a few people left, damn it. I have a practice test. This is our first practice test. I'm gonna have an answer key for this next time, because our test is when? A week from today. I will have an answer key for this. You do not have to turn this in then, yes? Please, dear God, don't turn this in. I've got enough paper. A really good way to use this practice test is try it like a real test. Anything you had trouble on, go focus on it. Next time, the first thing we're gonna do next time, I knew I wasn't gonna have enough time to do this anyway. I have a worksheet with some of this, examples of this. We'll do that together first thing, and then I'll open it up to whatever you guys want to talk about. You couldn't count while I was talking. You see that? Yes. Is there one? No. Not enough time for Monday is review for the test. Wednesday is the test. There's no time for anything. There will not be lecture after the test. You guys will be so brain fried you're not going to be able to. Well, we'll see. Maybe not. Oh, sorry. Don't let them know.
For my test collection, or